Welcome back. Now we will discuss the first and second derivative method, which is an extension of the previous sample and first derivative method for determining the peak value of the signal. We have seen in the last video lecture how the sample and first derivative method can be employed to determine the peak value of a signal and also the impedance of the given system. In this video lecture, we will go through the first and second derivative method. I hope that by the end of this lecture, you will be able to determine the peak value of a signal using the first and second derivative method. So we'll start with the introduction. What were the problems with the previous method that we have already seen? That in case of harmonics or in case of there are any DC transients, then the sample and first derivative method may not give a perfect result. So that particular problem is being overcome by this method. So coming to the introduction, the first and second derivative method, it is a technique which is used to determine the maximum of a particular function. So the first derivative is generally used, as you might have already seen in calculus, that let us suppose if f of x is a function, then f dash of x gives the maxima or minima of a function. And if it is, whether it is maxima or minima, that will be determined using the double derivative. If it is positive, then this function is going to be a negative one. If it is negative, then this function is going to be a positive one. This you might have used in your calculus, in your mathematics, engineering mathematics number 3. But here in power systems, we will use a similar type of method to determine the peak value of a signal. So when compared to the previous sample and first derivative method, this particular method, it reduces the errors which arise from subnormal frequencies, which generally are not eliminated in low pass filters. So how to determine the peak value using the first and second derivative method? Now let us suppose if I do have a signal V is equal to Vm sine omega t plus some theta. This is my voltage signal, let us suppose. Now the first derivative, as we have already seen, it is Em. So sine will become cos omega t plus theta, and the internal derivative is omega, which I'll write it here. If I do it double derivative, so I'll get omega Vm, cos will become minus sine, and again this omega will become an internal derivative, so I'll get here omega square, right? So if I do utilize these two equations, now you know what V dash by omega is equal to Vm cos omega t plus theta, whereas minus V double dash by omega square is equal to Vm sine omega t plus theta. So I will square these two equations and add these two equations. So this will become V dash by omega whole square plus is equal to, this is Vm square cos square omega t plus theta plus Vm square sine square omega t plus theta. So if I take Vm square common, then it will become 1. So I'll take it as so in this way this will become 1. So this is equal to Vm square. So I'll remove this square now. I will write this one as Vm square is equal to V dash by omega whole square plus minus whole square is, right. So what is Vm? So V dash by omega whole square plus V double dash by omega square whole square. Similarly, if I do have Im is equal to, if I know the values of Im, I can utilize these expressions for determining the peak value of voltage signal and also the current signal, right? Now as we have seen in the previous one, how to determine the magnitude of impedance. You know that impedance is always required because in distance relays we do require impedance. So I'll assume that voltage and current signals are available for me. So Z, first of all, let's try to determine the magnitude of Z, which is equal to V max by I max. You know, we have already seen that V max is given by square root of V dash by omega whole square plus V double dash by omega square whole square. Similarly, I max can be obtained from I dash by omega whole square plus I double dash by omega square whole square. From this, I can write mod Z, the magnitude of impedance, is V max by I max. So I'll take it as square root of V dash by omega whole square plus V double dash by omega square whole square by I dash by omega whole square plus I double dash by omega square whole square. So in this way, I can determine the impedance of the signal. The other method which I can employ the other one which I do require is a phase angle. As we have already seen that I'll take theta V and theta I. So V will become Vm sine theta V and I will become Im sine theta I, right? So if I derivate it, I'll get omega Vm sine theta V. If I double derivate it, I'll get, this is cos, right? Yeah. This will become minus omega square Vm sine theta V. Similarly here also, I dash is omega Im cos theta I, whereas I double dash, right? Because theta V was omega t, theta I was omega t plus phi. We have already seen these things in the previous method. Yeah, this is sine, right? Now, if you carefully see in this one, V dash by V double dash is equal to what I'll be getting. I'll be getting it as right. So I'll just inverse this one, and I will see here omega m will go out. So if I inverse and write it, so what I'll be getting, this is equal to sine theta V by cos theta V, and this is equal to tan theta V, right? Similarly here also I can write it as minus I double dash by omega I dash is equal to tan theta I. So what is theta V now? It is my tan inverse minus V double dash by omega V dash. Here it is theta I is equal to tan inverse of minus I double dash by omega I dash. So what is angle of impedance? Angle of impedance, it is theta V minus theta I, right? So I can directly take it as tan inverse of this one. Angle of Z is equal to theta V minus theta I, right? So it is tan inverse of minus V double dash by omega V dash minus tan inverse of minus I double dash by omega I dash. So in this way, if I do have first derivative and the second derivative, I can determine the phase angle and also the magnitude of the impedance of any signal. Now, what are the biggest advantages when compared to the previous one? If you can carefully see, in this one, since I am going with the second derivative, so a constant DC component has no effect since it is cancelled out from all the differential expressions. Right? It is differential expressions, okay? And the effect of non-zero frequency components due to any exponentially decaying offsets is consequently minimized because I am going with successive differentiation. And no mimic burden or related technique is required in many applications if I go with this one. But there is a limitation in this one. Any higher frequency components is present due to some sort of traveling waves, etc. They can produce significant errors, right? So if the omega value is high, then the error will also be very high in the first and second differential equations. So thereby, my output may also be erroneous. So that is the biggest problem with this one. So this particular method, conclusion, it is used to determine the peak value and phase angle of a pre-fault sinusoidal signal. So it involves first and second derivatives, just like your previous one, sample and first derivatives, but it is a little bit advantageous when compared to the previous method, because we will be able to eliminate the DC components. Okay, and also I hope that now you are able to describe this particular method and compare it with the previous sample and first derivative method. And this is your homework for you. We will discuss with the problem in the class. Okay, thank you.